All right, back so soon. Let's look at the reactions of alcohols. The first reaction, the main thing we're going to deal with today and in this chapter, is dehydration of an alcohol to form an alkene. Now, there's a phrase I want you to memorize. It's a little bit longer than this one, because if you have this phrase memorized, once you hear a part of it, you will then remember the rest of it, and then you will know exactly what's going to happen in a reaction. So here's the phrase: acid catalyzed dehydration of an alcohol to form an alkene. Memorize that phrase. Acid catalyzed dehydration of an alcohol to form an alkene. So now you know what happens what's the product if you dehydrate an alcohol? Oh, it forms an alkene. I get an alkene. Okay. But in order to get it to work, what must you also put in there? Ah, yes, acid catalyst. So if you have that phrase memorized, anytime you say, okay, I have an alcohol, I need to make an alkene, acid catalyzed dehydration of an alcohol to form an alkene, I know exactly what to do. All right, here's the deal. If you have an alkyl halide and react a nucleophile with it, we normally get a nice reaction, substitution reaction, SN2, where the nucleophile gets put on the R group and the leaving group leaves. The problem is, if we have an alcohol, ROH, how good of a leaving group is OH minus? Well, recall OH minus, strong base. Strong base equals good nucleophile. Good nucleophile equals bad leaving group. Yeah, OH minus is a horrible leaving group. If you have an alcohol and you add a nice nucleophile in there, you're not going to get anything. This reaction, big X through there, does not go. Hydroxide's a poor leaving group. You cannot get this reaction to go. So how do we get the reaction to work? We have to convert the alcohol OH, which would leave as OH minus, into a good leaving group. And we do that with strong acid. The first example is what I will tell you not to do. But one could we're going to find out later, well, you actually can do this if you want to. If you take your alcohol, ROH, and react it with a strong acid such as HCl, the oxygen here, the lone pair, will attack this hydrogen, kick off chloride, to make ROH2+. This is a good leaving group because if OH2+ leaves carrying these two electrons with it, that gives us H2O as our leaving group, and water is very stable. That reaction is going to go. All right. So we will come back to this. We'll look at it a little further in a bit. Let's look at our dehydration reactions first. Okay. So let's look at this molecule here. Take CH3, COH, there's our alcohol. CH3, CH2H. Note, this is a tertiary alcohol. If we start with this tertiary alcohol, note, written here is CH2H. That's just a fancy way of drawing a CH3. I'm going to need to single out this hydrogen. Because we're doing a dehydration, it is an elimination reaction. If you add H2SO4, you will end up eliminating this OH and this H plus are the two things that eventually get taken away to make this alkene, where you form a double bond between the carbon that contained the OH and a beta carbon that contained a hydrogen. You form that double bond plus water. That's why it's a dehydration reaction. You make water. Now, there is one slight problem. Sulfuric acid, nice strong acid, but it's really nice and soluble in water. You might run into some solubility issues or other issues with sulfuric acid. And so occasionally we want to use something, a strong acid very similar to sulfuric acid, that might help us with solubility issues or whatnot. In that case, we use para-toluene sulfonic acid. Okay, CH3 bonded to a benzene ring is toluene. We're going to learn next semester that if the SO3H group. The sulfonic acid group is on the opposite carbon of the methyl. That's para-toluene sulfonic acid. It has a very unfortunate abbreviation of TSOH. I don't like that because that would lead me to believe it's an alcohol. No, TSOH is a very strong acid. pKa of -7, the same pKa as sulfuric acid. But if you have a molecule and you have an OH on one carbon and there's an H on the carbon next door, add para-toluene sulfonic acid and you will form the alkene. All right, a few things about this reaction, this dehydration. One, it is regioselective. So note, here we have the OH on this tertiary carbon. We've got a beta hydrogens here and beta hydrogens over here. Note, this is a CH3 just as this is, so if these beta hydrogens will give us the same product as these beta hydrogens. But if you react this with sulfuric acid, you can get two products. Since we have two different types of beta hydrogen, we could snag one of these hydrogens to form a double bond between these two carbons and make this product over here. Or we could snag one of these two hydrogens and make a double bond between these two carbons where we'd have CH3, CH3 double bonded here to this carbon where we would get this one. Note, this is regioselective, but it follows Zaitsev's rule. The more substituted double bond is our major product because only one hydrogen on the double bonded carbons means this is a tri-substituted alkene. Two hydrogens, this is a geminal di-substituted alkene. Tri-substituted, more stable than di-substituted. Okay. And note in our reaction so far, we have looked at tertiary alkenes, we've looked at tertiary alcohols, secondary alcohols, because tertiary alcohols will react the fastest for dehydration. Secondary, meh. Primary alcohols, very, very slow with dehydration. All right, at this point you're probably saying, well, this is cool. I wonder what mechanisms these reactions go by. Well, secondary and tertiary alcohols dehydrate via E1. Primary dehydrates via E2. So let's look at these mechanisms. Let's examine how this works. And the good news is, if you really got chapters 7 and 8 really down nicely, chapter 9 here, there should be no surprises on how these mechanisms work. There's just one little thing at the beginning. Recall, what phrase do you memorize? Say that phrase that you have memorized. What's the first two words of the phrase? All right, acid catalyzed. That's the only new thing in these mechanisms, is we have to look at how the acid catalyzes the dehydration of these alcohols. That's the only new step. All right, so let's look at our E1 mechanism. The first thing we need to do, we know that this OH is a poor leaving group. We need to protonate it to make OH2 positive here. This pair of electrons here, lone pair, will attack the hydrogen of our sulfuric. This is just a fancy way to write sulfuric acid. This lone pair will attack that hydrogen, put the electrons on there, and now we get our protonated group OH2. And once we've done that, we've got our good leaving group. We made HSO4 minus also as the other product. But this is an E1 mechanism, and now we go right back to E1. We now have a good leaving group. And what's the first step of the E1 mechanism? That's right, leaving group leaves. So once you've made this good leaving group, it just takes off. It just goes on and leaves to give us a carbocation. And now we have a carbocation. Remember, with our E1 mechanism, a base must come in and snag a beta hydrogen. Recall, catalysts speed up reactions by lowering the activation energy, and they don't get used up. So if we start with H2SO4, we must end with H2SO4. Therefore, HSO4 minus will come back in, snag that hydrogen, and give us our alkene. So note, we started with our alcohol, we added acid, we ended up with an alkene, water, and we got that acid back again. All right, this is very important. Why we use H2SO4 or paratoluene sulfonic acid instead of HCl if you want to do a dehydration. Because HSO4 minus is a horrible, horrible, horrible nucleophile. We just go on and say HSO4 minus cannot act as a nucleophile. It can act as a base and take a hydrogen, but it cannot act as a nucleophile. Recall from last chapter, anytime you have the E1 mechanism, you can also have the SN1 mechanism happening at the same time. Not with acid catalyzed dehydration. It will only go via E1 because to have the SN1 mechanism, you need a nucleophile to attack the carbocation. A weak nucleophile needs to attack the carbocation. HSO4 minus cannot be a nucleophile. Therefore, it cannot attack the carbocation. It will only attack the hydrogen as a base. You only get the E1 dehydration. Cool. Paratoluene sulfonic acid, the conjugate base of that, also cannot be a nucleophile. So it is also very useful for doing E1 dehydrations. All right. So that's all fine and dandy, but what if you have a primary alcohol? Well, primary alcohol is going to have to go via E2. You recall E1 requires a carbocation. Tertiary carbocations, decent. Secondary carbocations, they're okay. Primary carbocations, too high energy, don't want to form. So if you have a primary alcohol and you want to do the dehydration, you still add H2SO4 as your catalyst, but it's going to go via E2, meaning you make this good leaving group, but since it's primary, it's not just going to leave. The leaving group isn't just going to leave on its own. The HSO4 minus must come in, snag that beta hydrogen, form that double bond with that bonding pair between the carbon and the hydrogen, becoming a double bond between these two carbons and kicking off that H2O. So this all occurs in just one substitution step. We've got but two steps overall. First, you get the protonation step to make the alcohol the good leaving group, and then just a regular old E2 elimination in one step after that. All right. But that does give us a bit of a problem, because when we look at this reaction, here's we got this molecule plus this and H2O. When we look at the enthalpy and the entropy, yes, we're looking at delta G. Recall delta G equals delta H minus T delta S. Delta G tells us the spontaneity of the reaction. Will it go under these conditions? When we look at the enthalpy, we see we have 8 sigma bonds here. Our product has 1, 2, 3, 4, 5, 6, 7, 8 sigma bonds. Or excuse me, our reactant, our alcohol reactant, 8 sigma bonds. Our products, when we look at this, we have 1, 2, 3, 4, 5, 6, 7 sigma bonds and 1 pi bond. So you can see during this reaction, it had the net result of changing one carbon-hydrogen sigma bond into a carbon-carbon double bond. Okay. But that carbon-hydrogen sigma bond became the pi bond of the carbon-carbon double bond. And recall, pi bonds are less stable than sigma bonds. So when we have this double bond here, yes, we've got the sigma bond, but the pi bond is not as strong as that sigma bond. If we've made a less stable bond, that means enthalpy-wise, this reaction is endothermic. Now, one could look at the entropy. Okay, well, let's look at the entropy here of this reaction. We've got one reactant, we've got 2 products. 2 products means more randomness can be had with 2 products. So the entropy is actually favorable because we make 2 products. However, recall from last chapter with delta G equals delta H minus T delta S, what's the more important term? Enthalpy delta H or entropy delta S? That is right. The more important term is the enthalpy, the heat of the reaction, which means since this reaction is exothermic, the equilibrium for this reaction lies to the left. If you take an alcohol and you add sulfuric acid to it, the equilibrium lies to the left. You just tend to get alcohol mixed with sulfuric acid. You don't make products. All right. But you say you want to make products. I need to be able to shift my equilibrium to the right. How does one shift equilibrium to the right? That's right. We get our little old robot, Le Chatelier. We need to do something that will push this equilibrium to the right. Not down, to the right, to the right. Yeah, there we go. That's why I named my robot Le Chatelier, because I can get the reaction to go whichever way I need it to go. All right, so how do we do this? Well, one nice way is if we remember our intramolecular forces, we know that OH, we can get hydrogen bonding, strong intermolecular force. Only van der Waals type forces here, only this is not a polar molecule, so we only have dispersion forces here, which means ethanol boils at a much higher temperature than ethene does. So what if we ran this reaction at a temperature lower than the boiling point of ethanol, but higher than the boiling point of ethene? Which means as this ethene gets made, since we're higher than the boiling point of ethene, the ethene will leave as a gas. What does Le Chatelier here say is going to happen if the product leaves? That's right. More of the ethanol will have to react with acid to make that ethene that we boiled away. Of course, that new product boils away, and so we can actually drive this reaction all the way to completion and not have hardly any unreacted alcohol simply by running this reaction at a temperature higher than the boiling point of our alkene product and getting rid of it as it forms.